Right. Hi everyone. Hope everyone's study week has been going well, and everyone preparing well for exams. So today we're just gonna go through the Maths 2221 and 2121 seminar. So my name's Jason, and I'll be running through the first half of today, and then Tim will be taking over for the second half. How the seminars are structured is that there are going to be two parts. So we're going to cover topic 1 and 2 today, and then cover topic 3 and 4 in the second seminar, which is on Friday. As I said earlier, today I'll be covering part 1, so linear ODEs, and then Tim will be covering the second half, which is dynamic systems. All right, let's just hop straight into it then. So, one other thing is that this would be recorded, and the lecture slides that we're going through today will be uploaded on the MathSoc website. So if you ever want to find that, you can just look for it there, and the recording should be on YouTube. All right, now we can hop straight into it. So the first couple stuff we're going to look at, which is part of linear ODEs, is just like a lot of definitions. So couple of the first thing is just what exactly is a linear differential operator. Commonly you can see it as a LDE, and is denoted with this capital L. And you can see the definition there. It seems pretty scary at first, but hopefully everyone is pretty comfortable with this. An example of this is, for example, L of u equals to u double dash plus u dash plus 2u. That will be a linear differential operator of order 2, because we have a second derivative here. So that's the first thing. The next definition is a singular ODE. So a singular ODE is one which vanishes on a given region. So we say it's singular with respect to the region if the leading coefficient vanishes. An example that we have here is xu dash minus u equals 0. This is singular because at x equals to 0, this first whole term vanishes. So it's singular on this range here. However, if we don't have that 0 included, so something like 1 to 2, now this ODE is no longer singular. So it's only singular on the range 0 to 1, but it's not singular on this range. All right, so that's the second definition here. Now looking at homogeneous ODEs. So hopefully everyone is comfortable with homogeneous ODEs. This is some stuff which would have been covered in first year courses. So homogeneous ODEs is essentially just when you have nothing on the right hand side. So the right hand side is equal to 0. A clear example is this here, where you have a linear ODE on one side is equal to 0. If we do have something on the right side, what we call that is an inhomogeneous ODE. So we have now that f term, so the function of x on the right. An example is just cosine. If we have a cosine here, it's now an inhomogeneous ODE. All right, so we can finally move on to our first question. And a question like this is not an exam question, but it's kind of to just get us warmed up to begin. So just solve the following homogeneous linear ODE. So the solutions here, we do go into quite a lot of detail. So it's supposed that u is equal to e to the rt, and we find the first and second derivative of u, and then just substitute it into the equation. So this is u double dash, this is u dash, and this is u, and we just substitute it into the ODE. And then we just solve for r, and we find r to be -1 plus minus root 5 on 2. So that's just solving this quadratic up here. And we write our final solution as just a linear combination of the two. Notice how we just keep it in R1 and R2 for simplicity here. I think in exams, probably just write it in. So write in the actual value of R1 and R2. So something like this. And this is just a linear combination. Hopefully this is pretty easy. We kind of just breeze through that. One thing I do want to mention is in actual exams, you don't need to go into, like, typically they won't ask a question like this, and this is just a step along the way to solve the final question. So something like this is not necessary, these two steps. You can probably just go straight into this line here that I've highlighted. So yeah, I guess that's the first example question that we have. Now we're going to look at the next. Before moving on, let's actually have a consideration of other possible cases, and namely double roots and complex roots. So the easiest case that we just looked at is if we have two distinct real roots. If we have a double root, which is R1 is equal to R2, instead of it just being a linear combination like what we have up here, we need to have it be something like this, or you can just write that as R1 as well. So this is R1. Basically, there is that t term in head so that we keep the dimension of the solution space to be 2. For complex roots, if we have the root equal to just say a plus b, or plus or minus. I wrote that in really weird notation. Let me redo that. So a plus or minus bi. Then the solution would look something along the lines of e to the a times c1 cosine b plus c2 sine b. And that would be the solution for the homogeneous equation. This is stuff that you can just quote. They do go into a bit more details about how exactly they get these in the lecture slides or in first year courses. So you can have a look at that or refer to that if there's any confusions. All right, so now we're going to look at initial value problems. So what initial value problems are is kind of, as the name suggests, you'll have some like differential equation, and you're also given some initial values. So for example, so we have a differential equation on AB, and it'll give us some values, u of a equals to something, u dash a equals to something, and so on and so forth. Example of this, a simple one, is just here's our differential equation. Our initial value is u of 0 equals 0. We skip the steps, but the solution will be this here. All right, so this is the initial value problem. We'll move on to some theories about them. And the first one is, if f is continuous on the interval that we're looking at, and we have an ODE like this, and it's non-singular, then the initial value problem has a unique solution. That's the first theorem. The second theorem here is if L is linear of mth order, it's non-singular on the interval, then the set of all solutions to the homogeneous equation forms a vector space of dimension m. So all solutions form a vector space of dimension m. I guess, what does this exactly mean? So what it means is that the solution space and the solution space is just, I guess, the set of all the solutions, or the space where all the solutions lie in. It has dimension m. And if U1 to Um are our solutions to the homogeneous equation, then if the solution to the homogeneous equation will then form a basis for that vector space. Essentially, what this means is any solution can be written as a linear combination of the solutions to the homogeneous equation. And that's kind of what we have here, and that's why we call it the general solution. So we write the general solution as a linear combination of the solutions to the homogeneous equation. All right, now let's have a tackle of a question. So it says solve the following homogeneous linear IVP, and note that this is the equation from before. So it's an equation from previous question, and we get given these initial values. All right, so before we saw that U of H equals to A e to the R1t plus B e to the R2t. And R1 and R2 were minus plus or minus root 5 on 2. But we'll just keep it as R1 and R2 for simplicity. Then what we get is we need to sub in the initial values. So U of 0 equals to 0. So we get A plus, which equals to A plus B. And we also get U dash of 0, which is R1A plus R2B equals to 2. So what we get is B equals to minus A, as well as A R1 minus R2 equals to 2. And then if we solve for A and B, you'll simply just get U of H equals to 2 over R1 minus R2 e to R1t plus 2 over R2 minus R1 e to R2t. So here we just substituted for A and B. Also, if you notice me skipping some algebra steps, it's because we do have these slides posted on the MathSoc website, as said before. So you can just find the more like formally written out solution like this on the MathSoc website if there's any steps. Like typically I'll only skip the algebra steps, so just like rearranging and stuff like that. So if there's any steps I skip, which you guys don't understand, you can find it there. Okay, so that's this example here. We'll move on to more definitions, I guess. Linear dependence is what we're going to look at. So if something is linearly independent, then if we have the sum of them to equal 0, this is only true for the trivial case when all of A1 to AM are all 0. Otherwise, we call it linearly dependent. So that's kind of our definition here. Hopefully that's fine. Once again, some first year concepts. All right, we'll move on to some new stuff. Don't quote me on my pronunciation, but the Wronskian is what I believe it's called. So the Wronskian is just we define it in terms of m functions, and it's an m by m determinant. So I guess that means it's a determinant of an m by m function. And this is the formula that it follows. Just looking at it, it seems a bit complex. Typically for our cases, we only look at it, I guess at most in 3 dimensions, typically just 2 dimensions, because we solve second order differential equations most of the time. But an example is seen here. So the Wronskian is just a determinant of this matrix here. For the 2D case, which is what we typically look at, that's the determinant of u1, u2, u-1, u-2, which is just equal to u1, u2 dash minus u2, u1 dash. I guess something that can be commonly confused is we say it's an m by m determinant, but when it comes out, it is just a single variable here. So it's not a matrix, it's just a single variable, like a constant, really. All right, now let's look at this. So a theorem relating to the Wronskians is linear independence. Skimming through this, it's just if the Wronskian equals to 0, then they are linearly dependent. If it's not equal to 0, then it's linearly independent. And note, we're taking the Wronskian of the m solutions to the ODE. So they're the solutions to this ODE. Next is these two lemmas. So if u1 to m are linearly dependent over an interval, then the Wronskian is equal to 0, which is pretty similar to what we had up here. So this, but kind of the other way around. And lemma 2 is that, so if we have a solution to an ODE of the form given, then this equation here is equal to 0. And once again, for these lemmas, the full written out proof is in the lecture slides provided by the course, but we just have a quick summary here. I'll put these theories to use. So first one is we have a homogeneous, show that the homogeneous solution to the following linear ODE are linearly independent. So this one here. I guess we first need to solve this to find what the homogeneous solutions are, and then we can use the Wronskian to show that they're linearly independent. We definitely don't need to use the Wronskian. There is other ways to show that it's linearly independent. However, for the sake of, I guess, practice, we're just going to use the Wronskian here. Pretty simple question. First, attain the characteristic equation. And I guess this goes back to what I was saying earlier, when we don't need to write the full steps of assume y equals to e to the rt or something along those lines. You can just hop straight into it and find the characteristic equation. So we get this here. R squared equals to minus 3, so r equals to root 3i plus or minus. So then our solution to that equation will just be, if you remember what we said, the general solution to a complex one is just if this is our if this is our r, then the general solution is just e to the a C1 cosine B plus C2 sine B. And in our case here, A is just 0. So then what we'll get is just cosine root 3t plus C2 sine root 3t. And I guess to be more precise, these are two separate solutions. So we can write this as y1 equals to cosine root 3t, y2 equals to sine root 3t. Now we just need to compute the Wronskian. So if we just rearrange this stuff, the Wronskian is the determinant of cosine root 3t, sine root 3t. And then you take the derivative on the next level down. So the derivative of the cosine is root 3 sine root 3t. Derivative of the sine is root 3 cosine root 3t. And that determinant, you'll figure it out to be root 3 cosine squared root 3t plus root 3 sine squared root 3t. And clearly this does not equal to 0. Namely, it equals to root 3. So then we have the solutions are linearly independent. Sorry, that should be not equal to. Alright, let's move on to a actual exam question now. So this one here. You can see what paper it's from. So the 2014 MATH2121 paper. First part is to prove that if we have two solutions, U1 and U2, then their Wronskian satisfies this here. So this is actually the equation that, the theorem that we looked at earlier. Oh, sorry, not theorem, the lemma that we looked at earlier. So we have to prove this lemma. And then the next part is to determine the form of W when U1 and U2 are solutions to this equation here. And I guess what it means by the form of W is just find W for this equation. Alright, so doing the first part, what we first get is, let's write out what our Wronskian would be. So our Wronskian is the det of U1, U2, U1 dash, U2 dash, which equals to U1, U2 dash minus U2, U1 dash. And then W dash, so that is equal to the derivative of what we have here. And just, I guess, using the product rule twice, you would get U1 dash U2 dash plus U1 U2 double dash minus U2 dash U1 dash plus U2 U1 double dash. And I guess the next thing is, by the definition of U1 and U2 being solutions to our equation here, we get that A2 U1 double dash plus A1 U dash plus A0 U1 equals to 0. And I guess the exact same thing with U2. Alright, now let's consider the left-hand side of this equation here. So a2 w dash plus a1 w. And that is then equal to, so a2 of what we have here plus a1 of that first thing we have up here as well. Then, as I said, we'll skip through a lot of the algebra. So what this ends up being is that u1 a2 u2 double dash plus a1 u2 dash minus u2 a2 u1 double dash plus a1 u1 dash. That's what we get it to be equal to. And if we see from, if we label these equation 1 and 2, we see from equation 1 and 2 that this here and this here aligns, while this here and this here aligns. So we can make that substitution. So u1 is minus a naught, u1 times minus a naught, u1 minus u2 times minus, this should be u2. And then u2 times minus a naught u1, and that's just equal to 0. So then we have proved that a2w1 plus a1w equals to 0, and that's as required. All right, the second part of this question says to hence determine the form of w when u1 and u2 are solutions of this equation down here. So what we have is, I guess clearly since this is the second part of the question, we probably need to use the first part, and namely we'll use this result that we proved. And just note here, a2 is equal to 1 minus x squared, and a1 is equal to minus 2x. So if we use this here, we can then find the form of w. So let's write that out. What we have is this result from earlier. Bring this down. And yeah, we have a2 equals this, a1 equals this, and we want to solve for w is essentially what we want to do. All right, so what we have is 1 minus x squared w dash plus or minus 2x w equal to 0. And this here is just a simple first order ODE, and it can be solved using the integrating factor. So for this, we'll take the integrating factor to be exponential of the integral of p of x, which is minus 2x over 1 minus x squared dx. And you'll see here that this is just equal to 1 minus x squared. So, well, I guess what we get here is just that d over dx of 1 minus x squared w that's equal to 1 minus x squared, w dash minus 2xw, which is equal to 0. So then w is just the integral of, I guess 1 minus x squared of w is equal to c, w just c over 1 minus x squared. And c is just some arbitrary constant. Okay, that's this practice question here. If there's any questions relating to this stuff, feel free to send it in the chat as well. We'll have someone monitoring the chat so your questions can be answered. Okay, so the next thing we're going to look at is reduction of order. So reduction of order is a theorem that we learn, and it's essentially if we get given one of the solutions, so we know a solution, we can find another one through this formula down here. So I guess this is essentially just remembering the formula and just solving an equation after you get one of the solutions. An example of this would be something like this. So firstly, we show that U1 is a solution, and then find the general solution using the reduction of order method. I guess the general idea is, first, show U1 as a solution. We get one solution. We can find the second solution through the reduction of order. And then we can just write it in the general solution form. So nothing too difficult here. All right. I think for the sake of time, we'll just kind of skim through the solutions of this one rather than writing it out ourselves. But essentially what you do is you substitute U1 dash and U1 double dash into this equation here. So you'll see that the U double dash, U dash, as well as U get substituted in. You see that's equal to 0, so that is a solution. The next thing is to compute the second solution using reduction of order. And to do this, we use the formula. So this is our formula here. You essentially just substitute that in. So you substitute that in. First, you compute the inner integral of this here. So that should have an integral sign. That should have an integral sign as well. Yeah, okay, so that works out. So have an integral like that. Solving it, you'll get this here. And essentially, now it's just integrating. So once again, I think we're missing the integrals. Sorry, that should be integral there. Integral there. Integral here. And then, that's what we get. So yeah, from here downwards is all just solving the integral and just plug it. We just plugged it into the formula. Okay, so that's this question. Next is educated guessing. So from the next couple of theorems we're going to look at is for a inhomogeneous ODE, we're going to see like how we can solve that and how to find a particular solution. So I guess what we essentially just do is make some guesses and hopefully that is the right answer. Typically they'll give us forms that we know we can guess, and one of them is just a normal polynomial. So here, if we have a linear differential operator of order m, so this here, and it has constant coefficients. If that's then for any integer r larger than 0, there exists a unique polynomial up of degree r such that L of up equals to r. We'll look at a practice question for this to see exactly what this theorem means. But I guess that's kind of what we have here. It's essentially just guess a polynomial of degree r such that it satisfies this equation. I guess, for example, if we have L of u equals to x squared, we'll guess that our particular solution is ax squared plus bx plus c. Something simple like that. The exact same idea for exponentials. We'll just make a guess. If we have an exponential as the as our inhomogeneous ODE, so on the right hand side that's our f. If it's an exponential, we make a guess that's an exponential over p of mu, where p is just the linear differential operator. Alright, so let's look at a question now. So this one here is just find a unique solution u to this ODE. And I guess kind of the general idea to solve something like this is first solve the homogeneous ODE and find the solutions. Second is guess a particular solution. And I guess in this case here, since we have a polynomial of degree 2, we will guess ax squared plus bx plus c to be our particular solution. And then using this, we can find the general solution, up plus and then the third is just, I guess, sub in initial values. That's the general step to solving something like this. Once again, for time, we might just skim through the solutions. So we find here, when we solve the homogeneous version, this is our characteristic equation, and you get these roots. So then the homogeneous the general solution to the homogeneous equation is just this here. So the linear combination of the two. Now that we have the homogeneous, we guess the particular. So we guess it to be ax squared plus bx plus c. And what we get here, essentially what we have here is we substitute up dash and up double dash to our initial equation u double dash plus 4u dash plus 3u equals to 9x squared. So you can see that this is, this here is up double dash, this is up dash, and this here is just up. So we sub that in. You'll compare coefficients to find. So yeah, comparing coefficients, you get a is equal to 3, b equal to minus 8, and c equals to 26 over 3. So then the general solution is just this here. Now we just want to sub in for the initial values, the initial conditions being u of 0 equal to 1 and u dash 0 equal to 0. We sub that in to find that C1's 2, C2 is minus 1 over 2. and then we get this to ultimately be our solution. And where this here is U of H, and this here is UP. For this here, once again, we'll kind of skim through this. So write down the general solution U of H of the fifth order linear homogeneous ODE. So for this, it would just be, you can easily see the roots of the equation to be 1 minus 2 minus 2i and negative I. So in general, the homogeneous equation just comes out to be this here. The next part is write down the form of a particular solution to the inhomogeneous ODE. So for this, it just wants us to find the form of the particular solution P, not the actual equation. So we don't need to find all the constants. So it's essentially asking us, what would our guess be to solve this solve this function here? So our guess would be ax squared e to the minus 2. So this looks pretty long and complicated, but we'll dissect where each of it comes from. So the function that we need to get is e to the minus 2x plus x squared cosine x. And then we have a homogeneous solution from before, which is this up here. So in order to make a guess, we do the exact same things that we said earlier, where for an exponential, we make a guess of an exponential. So that's where this first term comes from. However, you'll notice that there's an x squared in front now. The reason why there's an x squared is because in our homogeneous solution, we had e to the minus x and x e to the minus 2x. Sorry, c2 e to the minus 2x plus c3 x e to the minus 2x, which will kind of clash with this here. So essentially just multiply it by another x, such that they're not in the same space. All right, next is the x squared. And to guess for a normal kind of polynomial here, we just guessed a polynomial of that degree. So we make this guess bx squared plus cx plus d. And then finally, for this last part, x squared cosine x, the general thing to do is to do, I guess, what we have is an x squared multiplied with cosine, and the guess you make is the multiple of the two separate particular ones. So for x squared, it's ax squared plus bx plus c. For cosine x, the general guess you'll make would be a sine x plus b cosine x. So now you just do a multiple of the two. So that's what we have here and here. But once again, you'll notice the x in front of both of them. So the x here and the x here. And the reason why is because we already have cosine and sine x in the homogeneous solution. So we want to multiply by x again, so they're not in the same space. And that's how we get the particular solution here. And once again, as we said, it only wants us to find the form. So we don't actually need to solve for all these variable a's to j. Like, thank God we don't need to, otherwise that will take quite a while. Alright, we'll move on now to the annihilator method. So for the annihilator method, this is just a 2111 thing. So for any 2121 students, you don't need to worry about this. But the annihilator method is, imagine we have an ODE like this. We essentially want to annihilate the f of x by multiplying it by some differential operator. So differential operator is, as the name suggests, so it literally differentiates it. For example, d of x, that just gives us 1, so it differentiates differentiates x. And if we have d squared x, that would then lead us to, first, if we do 1, it's d of 1, then that's 0. So d squared x annihilates x. Similarly for d cubed would annihilate x squared. And we want to multiply both sides by some differential operator such that the right hand side gets annihilated and all that we get left with is this left hand side. And the solution to the homogeneous equation on the left hand side will then be the particular solution to the original differential equation. We'll go through a question related to this. So what we have here is this particular ODE, and it wants us to find a particular solution to it. So the general idea is we want to multiply both sides by some differential operator such that the right hand side would equal to 0. And essentially how we do that is we want to find something that annihilates e of x and something that annihilates sine x. So if we look at that, e of x is annihilated by d minus 1. We can just double check that. So d minus 1 of e to x equals to d e to x minus e to x, which equals to e to x minus itself, which is 0. And if we do the same thing for sine, it's annihilated by d squared plus 1. Once again, you can just check similarly to what we did above. And I did skip this earlier, but we can just factorize the left-hand side to give something like this. So if we multiply both sides by this function here, so we chose that because it annihilates e to x, so this part annihilates e to x, and this part annihilates sine x. Then what we get is we multiply both sides by it such that we get a to x times pd times y of x, giving us this equation here is equal to 0. And as we said earlier, solving this equation, this now homogeneous equation, will give us the particular solution to the original. And what we see here is the particular solution is of this form. Simply because you can easily see the solutions to the homogeneous equation in terms of the annihilator. Alright, so we get the particular solution of this form now. I guess that's not it. There's a couple things that we can note. The first one being that the first two terms here are actually just the solutions of the initial homogeneous equation. So what we have up here. So this is just solutions to y double dash minus 2y dash plus y equals 0. So that's not actually the particular solution. That would be homogeneous solutions to our initial ODE. So we ignore that part. And we also want to, so I guess this is the part that we get left after ignoring the first part. What we also want to do is just calculate what C3, C4, and C5 are. And we can do that by substituting into our initial ODE. So we sub in UP into y double dash minus y, 2y dash plus y. You sub in yp, so this particular solution, and solving it, you would get these coefficients. So our final particular solution is just this here. Okay, moving on is the variation to parameters. So for the variation of parameters, once again, it is just a theorem that you kind of memorize. So just say we have this ODE. Then let U1 and U2 be a basis for the homogeneous solution space. So essentially U1 and U2 are the solutions. And W of X is the Wronskian for U1 and U2. So this method is used to find a particular solution. And the particular solution is just this here. So V1 times U1 plus V2 times U2, where V1 dash is this formula and V2 dash is this formula here. I guess this just looks like a lot of, jumbo to memorize, but it is just a theorem that you just apply the formulas for. Let's look at a practice question for that. So it says use the variation of parameters methods to solve this. And I guess let's go through the general steps of how to use the variation of parameters. I guess what we first look at, if we look at the equation, couple prerequisites that we need to know is U1 and the Wronskian related to it. So we need to solve the homogeneous equation. And find U1 and U2. I guess we can also find the Wronskian while we're at it. I guess the second part is to find V1 dash, or V1 and V2 using the formula. And then finally, the third one is find U of X, which equals to V1x plus U1x plus V2x U2x. That's the general idea of how we want to use the variation parameter method. All right, so let's dive into this. So for this here, first step, as you said, is to solve the homogeneous equation. We get U1 and U2 to be e to the x and e to the 2x. And the Wronskian is just e to the 3x. The next thing is that this is straight from the formula. So the formula that we saw earlier, V1 dash is equal to minus U2 f of x over the Wronskian. So we have this be the Wronskian, e to the 2x would be U2, and this here is just f. And clearly V1 dash is just sine, minus sine, and V2 dash, once again, just straight from the formula, it's equal to e to the minus x sine x. Alright, so if we integrate both sides, we can find V1 and V2. And then that's step 1 and 2 of what we said earlier. So far, we found this, which is kind of the hard part. Step 3 is all we need to do and just combine it to find the actual formula. So if we combine it, we can find a particular solution where this is V1, this here is U1, this here is V2, and this here is U2. and then you'll get the final solution there. All right, now we're moving on to power series. So I guess what this theorem here says is if we have a linear second order homogeneous ODE, so typically you look at it something in this form, then what we get is if both P and Q are analytic at 0, we can find the power series expansion using something like this. So it's essentially saying that if you're analytic, you can find a power series expansion. I guess this also follows pretty nicely. So saying if coefficients P and Q are analytic for a given radius, then the formal power series of the solution of U of Z is also analytic for that region. So if this and this is analytic, then the solution in terms of the power series is also analytic for U. Pretty self-explanatory here. All right, so now we're going to look at kind of recurrence relation, how we actually utilize this idea. And what we get is typically we get given a ODE, and we want to essentially find the recurrence relation satisfied by this power series expansion. And we want to find a solution of U of 0 and U dash 0 for these bounds, I guess. They all of these type of questions follow a pretty set structure when you do it. And what that is essentially you want to find what U dash is, U double dash is, and then substitute it into this equation here. Once you substitute it, you rearrange and kind of manipulate the power series, and then you'll find something for U. So that's what we do here. So L of U is equal to this here is U double dash. This here would be Z U double dash, Z squared U double dash. This here will be minus Z U dash, and this here was just minus 3U. Jeez. Alright, just looking at the working out, I think we're missing a 3 here. And that will carry on to a 3 here as well. Alright, so I guess continuing on. So carry on our 3 that we're missing on. And what we did is essentially we just combined the last 3 sums. So if we combine this one, and this one here, we do get this sum up on the right. And essentially, if we change the bounds on our first sum here from k to k plus 2, then we can combine the 2 sums together. So if we finally combine the 2 sums, we get something like this. The whole point of this is such that we can get a recurrence relationship between AK and AK plus 2. So that's what we have going on here. We want L of U to equal to 0 by kind of the definition of the equation. So that means the coefficient here, the inside coefficients, this needs to equal to 0. And if that's the case, we rearrange to get this equation here. The question also asks us to find the solution for which u of 0 equals 0 and u dash 0 equals 6. So let's take that into account on this slide here. And we're kind of taking this into account. So we find u of 5, a of 5, a of 0 to be 0. So anything past a of 5, which are odd terms, are 0. Also, we find a1 and a3. Once again, all even terms are 0 as well, because we need a of 0 to equal to 0, as that's kind of what the recurrence is defined by u of 0 equal to 0. So then all even terms past this are 0 as well, and hence we get this to be our solution. Once again, I am going through this pretty fast for the sake of time. Hopefully, if there's anything you guys don't understand, send it into the chat. And if you guys still don't get it, you can have another look through the exercise once it gets posted. Alright, moving on to the next thing is the Cauchy-Euler ODEs. And for this here, we're now looking at singular ODEs. And singular ODEs is when the leading coefficient vanishes for one or more values in a given region. The first type is just a general ODE that we look at, and it's in the form when you have x squared and then x, and then I guess just a constant for the last one. And that's the general form of the Cauchy-Euler ODE. And I guess why we look at that is because there is a nice kind of solution that we can guess. We see that it is singular at 0. And if we apply the linear operator to x to the r, we get this here. And then we get it equation like this. So what we can see is that x to the r will be a solution if this inside part is 0. So that will be a solution to the homogeneous equation. So this is kind of just making an educated guess. And then we know the form of what it will be. Once we get that, once we find r, we can then find that the general solution is just the linear combination of the solutions for the homogeneous equation. And I guess what we said up here is that this is true if they're not equal. However, if R1 is equal to R2, we just multiply it by the natural log. So log base e of x. So this is basically just an educated guess. That's essentially what we're doing here. So we'll look at a question like this. Find the general solution of the Cauchy-Euler ODE. For this ODE here, it is a bit unique in the sense it's not just an ordinary Cauchy-Euler problem where you have this here. However, the fourth term, which is 13x to the power of 1 over 4, it doesn't correspond to like our educated guesses that we've made before. So rather we do just need to use the variation of parameter technique. So this is the equation that we get if we make for the Cauchy-Euler ODE. And solving that, you get r to be equal to minus 3 over 2 and negative 1. So we get the homogeneous solution to be what we have here. Y1 is this and y2 is this here. Now using the variation of parameters, So remember this is the formula. We just sub it into the formula where I guess u2 and u1 is just y1 and y2 that we found earlier. So if we sub that in, we can find the solution. I guess first let's calculate the Wronskian. So the Wronskian is just half x times -7/2. And what you'll get, the rest of it is just algebra, so we'll kind of skim through it. Computing v1 is just subbing y to f of x and w of x in, and you get this here. Once again, that should be an integral sign. And finally, v1 is just this. Do the same thing for v2, and then you'll get the particular solution to be this. And then that will be our overall solution. All right, the next example, or the next section, is a Frobenius normal form. And for this form here, it can be written like this. You see, this is pretty similar to what we just looked at for the Cauchy-Euler one. However, now we have a p of x and q of x, not just the z squared and z. I guess what difference it makes is that we can assume that near 0, well, if p of z and q are analytic at 0, and we essentially just write this in the format z squared u double dash plus z p0 plus q0 of u equals 0. And this is now in the form of what we saw earlier. So the Cauchy-Euler one that we looked at earlier. And note, I guess, that this and this are constants now rather than functions of z. Okay. And then from there, we can then just approach this using a power series. So we define the power series to be r of z multiplied by this, where r is the solutions to the integral equation. Give me one sec. I'm just looking at time, and we're going quite a lot over. I think after this question here, the rest of it is just, it's not exactly new theory. Well, it's just looking at two particular functions in particular, which is the Bessel and the Lagrangian. Once again, don't quote me on my pronunciation. So we'll go through this last practice question here, and then I'll hand it over to Tim. And once again, you guys can look through the lecture slides later on once it gets posted for the other two functions. All right, we'll go through this one. So it says determine the equation and the roots to the ODE. When apply that, x not equal to 0. So what we want to do is first, what we note is that p of x is 1 and q of x is x squared minus 1 over 9. So remember, what it is just essentially what is multiplied in front of our y dash and y. So that's what we get there. So we find p of 0 to be 1 and p of q of 0 to be minus 1 over 9. So then our new equation that we want to solve in the Cauchy-Euler form is just substituting here. So there's a 1 in front of here, which is just p of 0. And the minus 1 over 9 is just the q of 0. And then next, solving that, we get this equation here. So this is, remember, when we make y equals x to the r, we get this equation here. And then simply solving that, you get r is equal to 1 and minus 1 over 3. So that's from solving the quadratic above. The next thing we look at is, if we remember the question, the formula, it's essentially that y is equal to x to the r and sum of ak z to the k, x to the k, from 0 to infinity. So we essentially want to work with that. In particular, I guess the question does tell us that we want to find the first 3 non-zero terms of the power series about the larger one of the 2 roots. So I guess in particular here, we do want to work with r equals to 1 over 3, because that's what the question asks for. So the formula is this. However, we can bring that x to the r inside. So we get x to the k plus r. And this is pretty similar to the power series that we looked at before, in the sense that we just want to find what y dash is, we want to find what y double dash is, and then substitute these into the equation. So that's what we do here. We find y dash to be this, y double dash to be this, and then substituting into the equation here and manipulating. So this does look like a lot of algebra. So I just want to highlight where the equal signs are so you can see where each line starts and ends. I guess from here to the first equal sign, we made the substitutions for y double dash. We made the substitution for y dash here. And then we also made the substitution for y, which is across these 2 terms. The next thing is we just kind of combined all the terms into a single power series. Well, most of the terms into a single power series. So what we get is that this term here, as well as these 2, all gets combined in this large red one. And then we just simply simplified the inside here for the next step. And continuing on, what we essentially get is I think these slides are just a repeat of itself. But what we essentially get is that this is our final equation that we kind of need to look at. So, sorry, I'm kind of skipping through a bit fast. Let me show you what this is looking at. So what we're essentially looking at is the first two terms of this initial sum. So the first two terms of the sum is when k equals to 0, we get a naught x to the 0 plus r of 0 plus r squared minus 1 over 9. So this is just a naught r squared minus 1 over 9. For k equals to 1, you get a1 x to 1 plus r of 1 plus r squared minus 1 over 9, which is a1, sorry, I forgot the x to the r term here. So x to the r plus 1 of r plus 1 squared minus 1 over 9. So for our case, we have r is equal to 1 over 3. And then that means that this inside term here then becomes 0. So then what that means for a naught is that this can be anything. So that's why we get a naught is a free parameter. Next is that this inside here does not equal to 0. So a1 now has to equal to 0 for our equation to be true. So we can remove those two terms and look at the rest of the summation. So for the rest of the summation, this is our power series. So then we get this recurrence relationship here. So the recurrence relationship comes from that we need each coefficient to be 0. So we need this whole thing to equal to 0. And you simply just rearrange and we get the recurrence relation. Ultimately, we get this answer here. And that's just by finding the first three non-zero terms. And that's kind of what we get. All right, very rushed towards the end there, but we'll call it here. I'll pass it on to Tim to continue the next section.
Hey yo, hey yo, hey yo. Can we hear me yet? Is it working? We can. I'm gonna turn that off. So otherwise we don't have some back feedback. But guys, oh my god, guys, this is crazy. We're gonna be doing some differential equations. First off, absolutely massive props to the king himself, the mad lad Jason. Because he absolutely slayed his way through linear systems. But guys, guess what we're doing now? That's right. You know what comes after linear ODEs? We're going to be doing some dynamical systems. There's one thing I love more than derivatives, and it's when the derivatives are dynamical, okay? I like taking my derivatives and I love equating them. It's hectic stuff, okay? It's going to be crazy. Yeah, just to recap, if you weren't here with us at the start, we're splitting this over 2 days. The first part is today. The next part is on Friday. We've just had the incredible Jason go through linear ODEs. I'm going to be taking us through dynamical ODEs, and then on Friday we're going to be doing the other two topics, which are going to be poggers. Get keen for that. All of this is all recorded, so like you should be able to, as soon as the live stream's over, the entire thing will be available on the YouTubes, which is going to be bussin'. And the lecture slides will be available on the MathSoc website. I think it's linked down below in the description. I have the chat and all that sort of stuff right here. So feel free to ask questions and stuff. And it's gonna be a good time. Thank you, Kaleido, Nathaniel, and Wobo. It's gonna be bussin' today. All right, it's gonna go crazy. Let's just jump into it, guys. This is so cool. Okay. Dynamical systems. So state variables are natural variables xk equals xkt, which blah blah blah, cool. Basically, a state variable is just a function that changes with time. And sometimes we have lots of state variables that all change at the same time. So we put them in a vector because we're quirky like that. Now it's lovely because then we can differentiate that entire vector, and that gives us basically not just one differential equation, but a whole bunch of differential equations happening at the same time. Wow, guys, it's like there's lots of stuff going on all at the same time, which we like to call dynamical because things be moving, which is crazy. Now, if we set that equal to some forcing function or some like other thing that sort of determines how they change, we can call that thing f of x, and we've got some cool definitions down here. One of them is that we say if f depends explicitly on t, it's non-autonomous, and if it only depends on x, then it is called autonomous. But to be honest, we don't actually care about that because we have this Pogge's theorem, which says that if it's non-autonomous, we can just do some funky rearranging and make it autonomous. So like, you can just forget about autonomous, because I know I sure did until I wrote these slides, which is busting. Now, most of the stuff that we do in this topic, as like you would all probably know because we did test 2 together, most of the stuff in this topic, honestly, you don't see that many differential equations. A lot of this stuff is just the techniques, like the algebraic and the calculus techniques that we use to actually solve this stuff. So a lot of the stuff I'm going to be going through today isn't actually on how to solve the differential equations. It's just like the weird stuff surrounding the differential equations and the weird definitions that allow us to do stuff around differential equations. So let's just jump into that with my first fun busting thing, which is Lipschitz continuity. Okay, this is stuff that you only need to know if you're in 2221. There's a couple of those throughout this topic. I think first integrals as well is also only for 2221. So if you're in 2121, come back in like 10 minutes and we'll be done with this. What does Lipschitz continuity mean? Well, we say that a function f is Lipschitz continuous. Also, like Jason said, all right, don't trust me on pronunciation because, bro, this is a maths topic, not like an English topic. I don't know what the hell most of these things are, all right? Euler-Cauchy probably botched both of their names, all right? But basically, back to our big L, all right, we say that if we can find the difference between two functions at some 2 different points, if that's less than a constant scalar times the difference between the actual 2 points themselves, we call that Lipschitz. Essentially, it's like saying, all right, if you got some quirky function and you take 2 points, then the difference between these 2 points should be some constant time, like we should be able to find some constant that scales up the difference between these 2 points that is bigger than the difference between those 2 points. All of that like is quite abstract and quite weird, so I like to come back to these 2 theorems, which really help me to like understand what the hell Lipschitz actually means. It's basically just saying, it's kind of like a weird way, and like really narky pure maths people will like stab me for this, but not if I run away. Will stab me for this, but basically it's like a way of saying, okay, your function doesn't grow like doesn't grow unboundedly between 2 points, right? So we have these 2 busting theorems, one of which says if a function is Lipschitz continuous, it is also uniformly continuous. Cool. And then our other theorem is if a function is continuously differentiable on a compact interval, then it is Lipschitz continuous on that interval. Now, the reason that these 2 functions are so useful is because most questions that are to do with Lipschitz continuity are going to be one of 3 things. One of 2 things, really. Either prove or disprove that it is Lipschitz continuous, or find like what the actual constant is equal to. And this first theorem is great because it's really easy to use. It's really helpful to disprove that something is Lipschitz continuous by basically showing that at some point it grows unboundedly, i.e. it grows exponentially. And then the second one is really useful to prove something is actually Lipschitz continuous because this definition is like clunky and weird and gross. We don't like it. And so instead what we do is we use the second one, which is cool. We basically show, oh, okay, it's differentiable on this interval. Also, the interval is bounded, therefore, like it has to have some Lipschitz thing. And also, spoilers, most of the way that we calculate that Lipschitz continuity thing is using the mean value theorem, which is busted. So let me show you exactly what I mean. Might try and whip up both the theorems and the example at the same time. All right, so our question is f of x equals 10x Lipschitz on I equals 1, I equals the region between minus pi on 3 and pi on 3, and I2 equals minus pi on 2 to pi on 2. Okay, now for this first one, we can see that this is and also, sorry, I just realized I'm on like this really quirky color. Does anyone in the chat have a preference of color that I should use? Otherwise, I will. Ooh, what is this galaxy color? That's kind of gorgeous though. That's kind of stunning. I kind of like that. I might keep it on that. If anyone's got a suggestion, tell me what color I should change it to in the chat. All right. But okay, so if f of x is equal to 10x on that region, we can see that this region is a closed region, right? So thinking about our big condition is that we need like a compact interval. If we've got a closed region, all we have to check is that it's bounded, right? And you may remember that tan is looking a bit quirky over different regions. So tan looks oh, thank you, Nathaniel. All right, I will do whatever I want. You know what I'm going to do? Thank you. Okay. Yeah, so tan looks a bit quirky like this. Now, the big things we should be looking out for is, wow, tan is unbounded at those particular points. And if you remember back to like, I don't know, year 11 or year 10, whenever you learn this, because bloody hell, I know that I kind of low-key forgot it. But these happen at pi on 2. Tan equals pi on 2 and tan equals negative pi on 2, which means in this region here, we're like somewhere around here. And honestly, I'm going to get rid of some of these squircles because it's getting a bit confusing. But basically in this region here, we can see that, wow, it is actually closed and it is actually bounded. Therefore, purely based off that, we can say, yes, okay, cool, it is in fact Lipschitz on I1. So I guess what you could say is, I might change it to purple just because I feel like the galaxy color is giving me a little bit of brain. Basically we can say that, yes, as tan of x is continuously differentiable on this compact interval, then therefore it is Lipschitz continuous on that interval. And then similarly for this second situation, right, because we can see, first of all, this is not a compact interval, right, because it's not closed. Purely based off this, we can say, okay, it's not a compact interval. So then we can say, okay, we're probably not going to be dealing with this second situation. And in fact, looking at our graph, we can see, oh, wowzers, at pi on 2, as you get infinitely close to pi on 2 or negative pi on 2, we start growing unboundedly, like in both directions. And because of that, we can say, okay, it's probably not Lipschitz here. And that's exactly why, right? It's not uniformly continuous. We start growing unboundedly, and therefore it can't be Lipschitz. So a fancy way of saying that is, since f is continuously differentiable on the compact set interval I1, it is immediately Lipschitz on I1. However, it fails to be Lipschitz on I2 as no Lipschitz constant exists because tan is unbounded near pi on 2, or likewise, it's equally correct to say tan is unbounded near negative pi on 2, which is coolios. Likewise, even if we had a closed set that covered pi on 2, so say for example we were looking at the closed set like minus pi to pi, because even though this is a closed set, because it still contains these unbounded points, it's not a compact set. Just remember, a quick refresher, compact interval means it has to be both closed and bounded. And so therefore we still can't say it's Lipschitz, even if it's a larger interval there. So then the next question you might have is, okay, coolios, how do we actually figure out what the Lipschitz constant is, especially for this region here, right? So we know it's Lipschitz. How the hell do we figure out what that constant is? Now, because of the way that this thing is set out, it may give you kind of like triangle inequality kind of energy, or maybe if you've done complex analysis, kind of circle, I think, what's it called? The circle inequality. Guys, it's been like 2.5 years since I did complex analysis. There's like the other inequality, right? Basically, it might give you that energy as well. But in this case, what we actually can use pretty much every single time, because we've already proven that it is, or like we've already observed that it's continuously differentiable, we can go back to our like Math 1A or single variable calculus like knowledge, and we can say, oh cool, there's that bussin' thing called the mean value theorem. Let's go and steal that. Now, the mean value theorem, I think it says like if you've got like A and B inside this region, then like f of B minus f of A over B minus A is equal to the derivative of that at some point C. Now we can rearrange this into using the triangle inequality, we can rearrange this basically into a beautiful lovely thing with absolute values, which says f of A magnitude f of A minus magnitude f of B is less than or equal to sum f dash of C for C inside our bounded set there, times x minus, minus times like B minus A. Sorry, that's a bit chaotic. I will fix that up. And then essentially it's just our job to figure out, okay, what is this f dash of c? So essentially, because this takes exactly the form of that Lipschitz like thing, all we have to do is figure out, okay, first of all, what's the derivative of our function and what's some like c that's going to be biggest over all of them. Yeah, and so to do that, let's quickly differentiate our tan. So derivative of tan x is sec squared x, which is equal to, like, I guess 1 on cos squared x. Now we know in this region here that cos of x is going to be less than or equal to, cos of x is going to be greater than or equal to, cos of x is going to be greater than or equal to cos of pi on 3, right? Because pi on 3 is like the edge of this function here. So we can say it's going to be greater than or equal to cos of pi on 3. Cos of pi on 3, guys, this is really testing my mental trigonometry. That's greater than or equal to 1 on 2. And so then we can do some fun flippies. So we can say 1 on cos x is less than or equal to 2. Square that, we then get 1 on cos squared of x is less than or equal to, 4. And that is our Lipschitz constant, because we're essentially saying in this interval here, the derivative sec squared x is less than or equal to 4. So we can say for all c, for all values of c, that is going to be less than or equal to 4, and therefore our Lipschitz constant is 4. Hopefully that made sense to you guys, because I know that I was a little bit chaotic and all over the place, but basically the TLDR for Lipschitz is, if it's continuously differentiable on a closed and bounded, I think the key thing for me, right, is always just figure out, is your thing bounded, right? Like you could have a function, for example, like x squared, which is continuously differentiable, but if your like area is, for example, the real numbers, because x squared just goes off to infinity, zoom, 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 as like x becomes positive on like negative infinity, therefore it's not Lipschitz. So the key thing is, try and figure out in your region, is it completely bounded? Is your region closed? In which case you just differentiate it and find the highest derivative or the largest value of your derivative in that region. That's your Lipschitz constant. And if it's not, well, then you just prove that it's not bounded at some point, which is cool. Any other questions on Lipschitz, chuck them in the chat and we can chat about it later. Otherwise, I've got the full working out and full notes here. I think it all looks pretty bussin'. Now we have a very similar definition for Lipschitz continuity for vector fields, which is bussin', but the real reason we cared about Lipschitz theorems is because, and honestly, as with a lot of the topics in differential equations, we have some fun theorems like the uniqueness and existence theorem, and all of this cool stuff, but like for the most part, what you're going to get examined on in the test is like, can you actually solve the derivatives rather than do you know the uniqueness and existence theorem? Because I sure as hell know that I don't. And basically, the reason we care about Lipschitz is because if something is Lipschitz, then it allows us to do fun stuff with matrix exponentials. So, moving on to our next thing, basically, if we have a set of equations that looks like dx on dt, and sorry, I'm sort of speeding because I'm conscious of time and I want to get through all the fun stuff later on in this topic. We can say if we have like a special system of differential equations where we can write the differential equation, we can write the dynamical system in the form dx on dt equals a times x, we're able to do some very cool things with the matrix exponential. So if you are doing 2601 or 2501, you'll be now exhausted and bored to death of matrix exponentials. One of the fun things about this course is we don't care about the Jordan form. We like Jordan form, what this? I don't know what it is, to be honest. I did that course and then all of that knowledge just immediately went poof out of my brain. I haven't seen the Jordan form in a year. All right. But anyway, in this course, we do nice matrix exponentials. But in theory, right, you could do matrix exponentials for anything. What we care about is this definition of the matrix exponential, which basically uses the Taylor series expansion of the exponential, subs in the matrix, and then says, wowzers, let's like solve some stuff, right? And that's useful because, coming back to this set, if we have some kind of differential equation that has the form here, we can solve it as x of t is equal to e to the at times x0, which is why, essentially, we cared about any of that stuff that we've done so far, because if we can write a system of differential equations like this, we can solve them like this, which makes it like so much easier and so much nicer, and means we don't have to worry about all the individual functions. Coolios. So TLDR so far, we've done a whole bunch of definitions, but all it was leading up to was this beautiful idea of we can solve the differential equations as x of t equals e to the at times x of 0, which is very cool. Okay, let's do some quick stuff with that. Now, one of the fun things about this topic is it has a lot of links to linear algebra, and as a result, you can kind of expect to maybe see some kinds of questions like this, which involve linear algebra proofs. It's really the only, like, I guess, non-practical section of this course. So let's do this. So show that if AV is equal to lambda V, then e to the AV equals e to the lambda times V. This is basically showing us, this is kind of a truncated way of why we care about matrix exponentials in the first place, and it's kind of leading into our idea of diagonalization, which is going to be really, really nice. Now, in order to prove this, we're going to have to use two things. First of all, you may notice if AV is equal to lambda V, that means that V is an eigenvector of A with eigenvalue lambda, which is really, really cool. And a couple of useful results that we get from this is that A times V, if AV is equal to lambda V, then like A squared V is equal to A times V, which is equal to A times lambda times V, which is equal to lambda times A times V, which is equal to lambda times V, which is equal to lambda squared of V. And this essentially generalizes to this idea of A to the k times V is equal to lambda to the k times V. Essentially, it's like if you have an eigenvector and you're just constantly pounding your eigenvalue with that matrix, you get more and more and more eigenvalues, which is really cool and really bossy. Okay, now that is going to be super useful because if we want to do anything with matrix exponentials, I know if you're like me, you look at that and you go, okay, e to the a times v, that's kind of gross. I don't know how to do like matrix exponential multiplication. So what I would do instead is come back to my definition of what is the matrix exponential, because that allows us to express it in terms of a whole bunch of actual matrices multiplied together, which is something that we do know how to deal with. So we can write this instead as like 1 times lambda, 1 times a, 1 plus a squared on 2 factorial plus a3 on 3 factorial plus blah, 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 onwards and onwards times v, which I might just like quickly condense as like the sum of a to the k over k factorial times v, which is really, really useful because what result did we just prove? If I may have written it back up here, but we just proved that a to the k times v is equal to lambda times k to the v. Lambda to the power of k times v, which is equal to, so we can write that as like sum of a to the k times v over k factorial, and then we use this beautiful rule which says that lambda to the k times v over k factorial gives us that. We can then take our v back out, which gives us sum of lambda to the k over k factorial times v, and this takes exactly the form of our Taylor series for the exponential of just a scalar, which is essentially this thing over here, right? So this is now e to the lambda times v. Because remember, all of this that I did kind of rush over is just that e to the x is defined in Taylor series form, in converging Taylor series form, in perfectly converging Taylor series form as x to the k over k factorial, which is very coolios. So TLDR for this question, essentially we got our matrix exponential, which is honestly, this is a bit more of a linear algebra proof than a differential equations proof, but they can pop up sometimes because this topic especially has a lot of links and a lot of crossover between the two ideas. But essentially, we re-expressed our matrix exponential in terms of a sum of lots of powers of a, and that allowed us to do normal linear algebra things, which is very, very cool. As always, the full proof is written down here if you are interested, but let's get into the real meat, which is how do we actually calculate the matrix exponential. Now, in this course, we sort of have three main systems of calculating the matrix exponential. Now, because we don't have to deal with matrices that are of the Jordan form, or we don't learn about the Jordan form in this course. We never have to do those really gross, disgusting matrix exponentials. So the way that we usually do this is by diagonalizing the matrix somehow. So hopefully by this point you all have learned how to diagonalize a matrix, but just really quickly, the way you do it is you construct a diagonal matrix made up of all of your eigenvectors of your matrix, and then you construct another matrix which just has all the columns made up of the eigenvalues, and then you can say that your matrix, your original matrix is equal to Q times whatever your diagonal matrix is times Q inverse. And the reason that this is so bussin' is we have a really cool theorem which says that e to the power of a, that matrix exponential, in general is equal to EQ times e to the power of all the diagonal matrix, so e to the power of your diagonal matrix, times that Q inverse. And that's really cool because e to the power of your diagonal matrix is just all of the values of your diagonal matrix put to the power of e. So like e to the power of lambda 1, and then e to the power of lambda n, which we love that. We love diagonal matrices. So the first way, coming all the way back up to our idea of why we wanted to, how we wanted to solve this, essentially, the first way that we can do it is if our matrix is so I guess the really trivial case is if our matrix is diagonal, then this solution here is just all of the lambdas placed to the power of e. If our matrix is diagonalizable, then all we have to do is diagonalize it, and then we can calculate our matrix exponential, admittedly through a decent amount of matrix multiplication. I don't know if you guys remember test 2, that felt like more just matrix multiplication than actually having to calculate the derivatives of stuff. But essentially, our three methods usually for calculating the matrix exponential is either diagonalize it, which is really cool, because if we have a diagonalizable matrix, then that's lovely. If A can be written as a sum of two commuting matrices, so what this often refers to is if we have a matrix that looks like 2, 0, not 2, 0, sorry, if we have something like 2, 1, 0, 2, this could be written as 2, 0, 0, 2 and plus 0, 1, 0, 0. Now, don't quote me on this because I haven't had enough time. I just made this up on the spot, right? I haven't had enough time to check if they do actually commute with each other. My guess would be that they probably do. But in this case, if, say, it's not actually diagonalizable, we can then notice that this matrix is nilpotent. Essentially, we're saying that 0, 0, 0, 1, like that squared should be equal to the 0 matrix, which means that e to the, like if this is, let's call this matrix B, e to the b times t is just going to be equal to b plus t times b, which is really nice, because that then allows us to calculate the matrix exponential really nicely. And then, of course, if neither of those two methods work, we can use that funky algorithm, which is really cool and really bussin'. So those are our main three ways of diagonalizing matrices, sorry, of calculating matrix exponentials. Either we diagonalize it, we split it into these two different matrices, one which is diagonal and one which is nilpotent, and then otherwise we use the fun algorithm, which is really cool. I'm not sure if the algorithm is in 2121, but in 2221 we've gone through it a number of times. So the TLDR of all of this topic is if we have something that looks like this, e to the a times x0, I'm sorry that I'm speed running a lot of this stuff, then basically, sorry, e to the ax, then we can solve it really nicely as just x is equal to e to the a times t times x0, and then we can do all of our lovely linear algebra stuff to calculate what e to the a times t is. So basically, honestly, 95% of this entire topic is just can you find the exponential of your matrix, and most of that comes down to like, can you diagonalize it? or can you work through the algorithms to diagonalize it, which is really cool. Got any other questions on that? Chuck them in the chat. But let's move through to our idea of equilibrium points. Now, this whole next topic falls sort of under the idea of stability, because one of the most important things for dynamical systems is we care about what's going to happen to the system over time. And most of the time, we care about one of either three things is going to happen. Either as time moves on, our system is going to rocket off into infinity, i.e. we call it completely unstable. It's either going to converge down into some like solid state and continue at that like solid stable state for the rest of its life, at which point we would say it's in equilibrium or it converges, or it's just going to continuously oscillate for the rest of its life, where we would say it's like partially stable or marginally stable. Now, one of the key details in this is the idea of equilibrium points, because these are the points, we define them as equilibrium points because they are the points where you could potentially stay at until infinity. And the reason we could stay at until infinity is because they're the points where our derivative isn't changing, i.e. these would be the points where we would be staying still for the rest of our lives. And to solve them, it's fairly similar to like optimization in single variable. All we have to do is solve for where the derivatives are zero. Most of the time, this is a fairly nice, easy thing to do. Sometimes it's a little bit yucky. Sometimes it's quite not nice to do. We have a nice analysis-y kind of definition for our stable equilibrium and stuff, but basically we've got a couple of different kinds of equilibrium. Our stable equilibrium is basically like if we have some point and you start somewhere close enough to that point, eventually you will always converge into that point. That's what a stable equilibrium is. An asymptotic equilibrium is basically as time moves on, we will reach that point. And then, yeah. So let's consider the linear system. dx on dt is equal to a times x plus b, where a is non-singular, i.e. a is doesn't have determinant equal to 0. Then the unique equilibrium point, i.e. a is invertible, is given by a equals minus a inverse times b, and the solution to the system is given by this, which brings us to our lovely variation of coefficient stuff. Now, we've got a couple of definitions to do with stability. So let's say A has a set of eigenvalues, which are given by lambda 1 up to lambda n. Then our particular equilibrium point, A equals minus A inverse times B, is, we call it stable, if all of the real components of your eigenvalues are less than 0. If you're curious as to why, essentially this is because when we go about solving all of our systems, usually our system will take the form like e to the like real part of our lambda times like cos times the imaginary part, blah blah blah. And if this real part is bigger than 0, then that means that the exponential part is going to zoom up to infinity. And if the real part is less than 0, then that means it will go down to 0. So basically, if all of your real parts are less than 0, it's going to be stable because all of your components of your system will go down to 0. We call it asymptotically 0 if some of them are, so asymptotically stable if they're all strictly less than 0, because remember, if some of them are equal to 0, that means you will get the point where it sort of stays within a particular region, but it could oscillate. And if at least one of your lambdas is positive, if at least one of the real parts of your eigenvalues is positive, that will then mean that your system will shoot off to infinity because you'll have some positive exponential, which is not super great. Which is why we call it an unstable system, all right? We love stability, okay? We love, in the real world, we generally love stable systems because, you know, non-stable systems, we don't love them. Okay, classifying 2D linear systems. So given the system there, we can basically come up with a whole bunch of things. I'm just quite conscious of time. All of these definitions are great, but a lot of the time we've got a couple of different stable node types. We can have a stable node where you might have particular lines of stability where you converge inwards. Now, I do actually want to quickly note on how you will draw these phase diagrams, because I know that they are kind of munted. So oftentimes when you solve this system, you'll be able to find like two lambdas with corresponding eigenvectors, like lambda 1 and lambda 2 with like their corresponding eigenvectors. Those two would be degenerate, so let's change it to like -1 and 1 instead. And then basically you can draw out lovely little phase diagrams. Let's say that lambda 1 is positive, and lambda 2 is negative. That would then mean that you can draw these two lines along each of the eigenvectors. So this one will go through the origin like that, and one of them will go through the origin like that. Sorry, I just had to do some basic mental arithmetic in my head, basic graphing in my head. Now, if this first lambda is less than 0, that means it's going to be stable, so we can sort of draw some little arrows on this one pointing to say, oh wow, it's going to go in towards 0. And then if our other one is greater than 0, that means that it's going to be unstable, so it's going to have little lines pointing away from it. And then you can sort of just imagine that we've got kind of this like big vector field that follows these lines. You can sort of imagine, okay, let's say we have a vector that starts in this point here. Well, the closest eigendirection to it is pointing outwards, so therefore we would probably move away like that. But if we started over here, right, initially we might be moving in towards the origin, but then suddenly we cross around to the other side, so we're going to loop around like that. And in this case here, we actually do sort of have a big field that looks like that. I guess it's almost like you can kind of imagine them as a bit like electric particles. I know that this is going back to like lovely engineering definitions, but like you can almost think of these eigendirections as being like the directions of like electric fields, and your motion of your particles, or the motion of like charged particles, sort of shows you where your different trajectories are that your positions could go. But we can notice here, right, that if you started, for example, directly on this line here, then you would zoom in towards the origin, and then once you reach the other side, because it's now still pushing you in, you would just chill there, right? Which is why we call a equals 0 the equilibrium point in this case, because it's that one point that you could chill at. However, it's not a stable equilibrium, because if you still have any kind of momentum, like let's say you come into that point from over here, then oh no, you're going to still shoot off into the other direction, and because like the other eigendirection is unstable, and therefore we call this a saddle point. I've included some diagrams of some of the other different forms of nodes that we can have. We've got a stable star, unstable saddle. We've got cool little like spiral things which are bossing. But let's actually do a quick practice and let's try and solve the following system of linear equations. Okay. This is kind of the typical question that you might expect to get in your exam, because it's actually got a set of differential equations that we want to solve. So in order to do that, we have to first of all write this as in a matrix form, right? So we can see that this is kind of like writing x dot and y dot is equal to 1, 2, -5, -1. This is just coming from looking at all the coefficients times by x and y, which is in that form. X dot is equal to a times x, which means wowzers, we can solve this if we can solve x equals e to the at. I will just say though, that this will sort of depend on us being able to find the eigenvalues and eigenvectors. So let's quickly go ahead and do that. So ignoring the question for a second, let's do linear algebra time, all right? Super exciting. So if we have a equals to 1, 2, -5, -1, because we are second year, right, you should all be able to find the eigenvectors or eigenvalues of this thing relatively quickly, right? So we can use the fact that the trace of A is equal to 0. Ooh, that's kind of quirky. We can then, is that right? Did I copy that right? Okay, we did. Oh, this is fun. Okay, and then the determinant of A is equal to -1 plus 10, which is equal to 9. Cool. So that basically means we're looking for two eigenvalues that when you add them together, they give you 0, and when you product them together, you get 9. I'm really feeling like maybe I messed up somewhere here, because I don't want to say that like wowzers, so please in the chat, if I did make a mistake, call me out on it, all right? My mental arithmetic sometimes be lacking, distinctly lacking. Anyway, we want two eigenvalues that sum together to give you 0 and product together to give you 9. And the easiest, I guess, two that I can think of would be like plus or minus 3i, right? Because those two add together to give you 0. And when you product them together, let me just get out my complex number calculator. Cheeky flex. That gives you 9 as well. The logic behind that, I feel like, is just maths. Alternatively, you could go through and find the other two things. I guess you could almost write it as like x plus y equals 0, which means you have to have x equals minus y. And also then the product of them, so x times y is equal to 9, i.e. that's the same as having like minus x squared equals 9, which therefore gives you x has to equal minus 3i. Or plus or minus 3i, sorry. Coolios. So now we've got our eigenvalues. Let's go about finding our eigenvectors, which is really cool. So in order to do that, we have to subtract. Let's maybe find the eigenvectors of let's do minus 3i, right? Well, let's actually do plus 3i. Let's do plus 3i. The way we do that is, of course, we do like lambda times I minus a. So in this case, we're going to get 3i minus 1, minus 2, minus 5, and then 3i plus 1. And we want to find some kind of x and y where this is equal to 0. Now, if you can do that in your head, big props to you. You are evidently gigantically brained. Let's write out these equations then. So x times 3i minus 1 minus 2y is equal to 0, which then gives you y is equal to x on 2 times 3i minus 1. And so I guess from there we can then just pick two of our values, right? So we could say, let's set x equals to 2, because that makes things nice. We can then say y has to be equal to 3i minus 1. So I guess then that gives us our eigenvector of 2 and 3i minus 1, which, you know what, in hindsight, that was not horrifically hard to solve. Let me just quickly check that, yes, that will indeed give us our eigenvalue, our eigenvector by multiplying that across by the second matrix. So minus 10 plus 3i plus 1 times 3i minus 1 gives us, actually, mental maths. Actually, I'm going to do it on my calculator. 3i plus 1, 3i minus 1 gives us minus 20. Okay, something has gone suspiciously wrong here. What have we done? What have I done? I could have made a mistake at any point in this calculation. Oh, it's because that minus 5, I forgot to make it negative when I made. Yes. Oh, thank you, Wonbin. Big shouts. Cool. Wonbin got my back. Okay, yes, my 5 is wrong, which means this should be positive 10, which means that equals 0. Which coolios, that then means we now have an eigenvector and an eigenvalue. So 3i has its corresponding eigenvector to 3 minus I. Now the reason that is so cool is because when we have a complex conjugate set of eigenvectors and eigenvalues, we can write the solution. So the solution takes the form x of t. Basically, it means we don't even have to do no matrix exponentials or anything, right? We can use this really quirky formula, which I feel like we went through all the way back in like week 1, which basically says we can have this thing which is like r e to the lambda times, oh man, I think I've got it in the slides down here somewhere. Cool. Yes, here we go, right? So we have lambda equals 3i and we have v equals 2 minus 1 plus 3i. We can write the general solution as just being c1 times the real part of e times our vector, and then plus c2 times the imaginary part of all of that stuff multiplied together, which is really cool. So the way we're actually going to expand this is using Euler's formula. So c1 times converting e to the 3it is equal to cos times 3t plus I times sine of 3t. That will then give us this thing is equal to e to the 3it times 2 minus 1 plus 3I is instead equal to 2 cos of 3t. And I do realize that it is 1 o'clock, so I'll try and wrap up reasonably quickly. I'm sorry, y'all. What can I say? Differential equations, just too spicy. I love it too much. Times minus cos 3t minus I sine 3t plus 3i cos, I'm going to need to give myself some more space, times 3t minus 3 sine 3t. And then to actually solve our equation, we take the real part. So the real part will be made up of u and u and u. And then the imaginary part is made up of u and u and u. So that then gives us our general solution as being x of t is equal to 2 of cos 3t minus cos 3t minus 3 sine 3t, c1 plus c2 times our minus section, so minus sine of 3t. This is, of course, all assuming that all of my math is right, which, like, once again, y'all in the chat, please fact check me on that. Times 3 cos of 3t, which, hell yeah, that goes unreasonably hard. So yeah, so what we can see from that is because our eigenvectors were purely imaginary, we end up with this solution, which is purely oscillatory, right? It's never going to go zoom, zoom, zoom upwards or downwards or anything. It's just going to chill, oscillating, being a quirky boy by itself. Which is coolios. I feel like I probably then did make a mistake because that doesn't look exactly like I had written it to be. But that is a-okay. I missed a 2 here. That's one of my big issues. But anyway, guys, that is very cool. Let's move on to our last topic, which is 2221 only. So if you're in 2121, you can feel free to head off. Love you, hugs and kisses. But it's this idea of first integral. Basically, if we have a big, yucky, non-linear problem, we can reduce the order of our system and make it slightly nicer to solve by finding essentially some region where g of x of t is constant for all of our solutions. Basically, it allows us to limit our problem to a particular space. And that's cool and all, but in classic 2221 style, all we actually care about is how do you actually find these things in the first place? Because it's a bit weird. Now, geometrically, g is a first integral if it satisfies that when you take your gradient of it, that gradient is perpendicular to f of x. Now, most of the time, usually you will either be given your first integral or you can do some quirky maths to try and figure it out. So let's have a go. Let's wrap everything up by doing a practice question. So find a first integral g of the system of nonlinear ODEs dx dt is equal to f of x, where f of x is equal to x minus x times y on xy minus y. Check your answer by computing delta g of x times y of x. Sorry, times f of x. Okay, so essentially what we want to do is we want to find some kind of function where g, in this case, because our two variables are x and y, we want to find some g x times y equal to c. Now, part of the reason that this is called first integral is that this may vaguely remind you of when you integral some kind of thing, you get c on the other side. And that's sort of, I guess, kind of the logic that we're going to use here. So we're going to do some quirky kind of maths here to figure that out, right? Because you can sort of imagine if we were able to figure out what dy on dx is equal to, we could then integrate it, and that would give us some fun plus c, which would hopefully, essentially, if we can find dy dx is equal to something, we could then solve that to integrate dy dx, and that would give us y is equal to some x plus c. It probably won't exactly look like that, but the TLDR from this is essentially we're going to do some very cheeky maths by finding out what is dy on dx equal to. Now, we can say that dy on dx is equal to, sorry, not dx on dx, we can say dy on dx is equal to, this is pulling out some rates of change as stuff. So we can say that that's dy on dt times dt on dx, which is really, really cool. Because we can actually figure out what both of those two things are, right? Because remember, f of x is equal to like some x times some y, or like some x of t times some y of t. Basically, it tells us that like x of t is equal to x minus x times y, and y of t is equal to x times y minus y. So then we can do some differentiating, which I love. I love to differentiate stuff. So let's do that. So first of all, dx on dt is equal to, dx on dt is equal to, let me back up a step. I realized I just said a whole bunch of stuff that I don't actually think is true, right? Because we can actually come back to this thing here. We can say, when I was dealing with x of t, I realized I may have actually been talking about dx on dt, because we can actually write this, and I'm sorry, you'll please forgive me. We can actually write this equation back over here as dx on dt, and then dy on dt is equal to f of x, is equal to f of x, which is then equal to our lovely x minus xy and xy minus y, which basically tells us, oh wow, we don't actually have to do any work at all. We already have that dx on dt is equal to x minus xy, and we already have that dy on dt is equal to xy minus y, which is really cool. So let's go ahead and substitute those two in. So dy on dt is equal to xy minus y. So this is going to be equal to xy minus y divided by our dx on dt, which gives us x minus xy, which is really cool. Because now, remember, all the way back, we were like, okay, if we can figure out some dy on dx is equal to something, hopefully then we can integrate it, and maybe if we can integrate it, we'll get some c, which will give us some kind of first integral. Let's see if that happens. So we now have dy on dx is equal to xy minus y on x minus x times y. Let's try and factorize this out to make it separable, so we can have y x minus 1 on x 1 minus y. So let's move all the y stuff onto one side, all the x stuff onto the other side. So we now have dy times 1 minus y on y is equal to dx times x minus 1 on x. Let's maybe simplify that a little bit. So dy times 1 on y minus 1, which is cool. We love integrals and stuff. And then dx is equal to 1 minus 1 on x. And guys, we finally made it. We've gotten our things into a point that we can now integrate this, all right? And remember, if we can integrate it, that means we'll get some plus c, and hopefully, assuming we can do algebra correctly, then we will be able to actually find a first integral. It will have all been worth it. It won't be suffering anymore. Okay, so let's integrate both sides of this bad boy. If we integrate the dy side, we now get ln of y minus y, and then if we integrate the x side, we now get ln, we get, what do we actually get? We get x, my just basic integrating skills just jumped off of the table and died for a second, which is cool. So now we have this whole bussin' looking thing, which is lovely. Love that, thriving. So then all we have to do is solve to try and get C on one side, because the C, shockingly, this time is actually what we're interested in. We care about C. So moving everything onto the other side that doesn't have C, we now have ln y plus ln x minus x plus y is equal to C. We can combine these two together to give us ln of x times y minus x plus y equals c. Let's put everything to the power of e, so that then gives us xy e to the minus x plus y is equal to e to the c, which is of course equal to like some other constant. And y'all, we have done it. All right, we've finally got something that has x and y on one side, and we've got a constant on the other side. At long last, we have found our first integral, which would be helpful in actually figuring out, here is a surface on which the trajectories are constant, which we love that. Very, very froth. I froth that. which is lovely. So then I guess to wrap up, we can actually check, okay, is this a first integral? Because basically so far I've done a whole bunch of quirky maths that seems to have just done some magic stuff. Let's actually check that the magic that it did actually work. So if we take the gradient of this, so remember the gradient takes the partial derivatives of each of our things and puts it in a vector. So first of all, if we differentiate, oh, it's going to be gross, y'all. Okay, if we differentiate with respect to x, first we end up with y to the minus x plus y, and then I think minus xy to the minus x plus y, and I think we get exactly the same thing in terms of y, if we take the partial derivatives with respect to y. So x to the minus x plus y, minus xy to the minus x plus y, which froth that, okay? Love that. Am I able to move this? I'm really sorry, guys. I've been sort of like deleting everything as soon as I don't like it anymore. I could have done that the whole time. That's crazy. Um, and then finally, we're gonna dot product this gross, yucky looking thing with our original function to see is it equal to 0. So if we dot that with, oh, it's gonna be gross. I don't want to do this. Anyway, this is my mentality basically whenever I see those gross questions at the end of exams. I'm like, come on. I don't want to do that. Okay, so if we dot that, we do that dotted with x minus xy, xy, xy minus y, we end up with x minus xy times, and I can actually factorize out a y. Oh, and actually I can make it slightly easier, right? I might actually go, before I jump into this, right, I'm actually rewrite what my gradient looks like to make it slightly nicer. So because we can factorize out, e to the minus x plus y from each term. And then factorizing each of the above ones, we then have y 1 minus x, and then we have x 1 minus y down the bottom. Okay, maybe I was overreacting. We can then dot product that with x 1 minus y and y 1 minus x. We dot product all of that together, we end up with e to the minus x plus y times, then expanding that all out, we get xy, 1 minus x, 1 minus y, plus, oh no, y'all, this is suddenly not looking so hot. Except I made a mistake down here, down this one right there. It's classic Tim. Your boy done goofed. This one should actually be x minus 1. Wonbin, you should have picked up on that, alright. No, I'm kidding. We now have yx minus 1 down the bottom here, which means we now have plus xy times 1 minus y, times x minus 1. But of course, here we have 1 minus x, here we have x minus 1. That means that these two are negatives, which means all of this disappears off to 0. So yes, indeed, this thing over here is a first integral of the system. And with that, we have done first integrals. I think I've got a whole solution of this thing here, which is very cool. We love that. And that brings us to the end of today's lecture. So just quickly recapping everything that I went through today. First of all, Lipschitz stuff, most of the time it's just testing, is it differentiable and is it bounded? And if it is, yes, cool, we get a whole bunch of fun stuff. From that, we then calculate the matrix exponential, which usually just involves diagonalizing your matrix, and hopefully you're all good with that. Stability, if your lambdas are less than 0, then you are usually stable. If they are like lie on the imaginary axis, then they're usually oscillating, and if they are positive, then it is unstable. During those things are fun as well, and then finally we can solve them to get either exponentially increasing, exponentially decreasing, or oscillating solutions. And then finally, first derivatives, first integrals, lots of maths, coolios, we love maths, I love derivatives and differentiating things. But thank you all very much for coming. If you want to give us some feedback so that we can improve, please scan the QR code, that would be very bussin', love you all so much. Part 2 is coming on Friday. We're going to go through more of our boundary value problems and then everything to do with Fourier, because what can I say, I love Fourier. Once again, big props to Jason for part 1, and if you're keen for more derivatives, like I think that I am, because what can I say, I love derivatives, I will see you on Friday. It's going to be keen, get keen, love you all very much. Have have a lovely week, honestly, and get keen for next Saturday, 2 weeks. All right, it's gonna go unreasonably hard. Hopefully not unreasonably hard. Hopefully it'll be unreasonably easy. Anyway, I'm waffling. I'll see you guys. Hugs and kisses.